So today's talk is about exoplanets, their properties and how you find them. And let's just be clear about the definition. When I'm talking about an exoplanet, it's the term we use for a planet that's in orbit around a star that is not our sun. So they're not part of our solar system. And this term exoplanet is one that you would not really have heard 20 years ago. And yet now it's in everyday use. And that reflects how quickly this field has changed from those first discoveries in the 1990s to the phase we're in now, where we are discovering new planets every day, every week. We know about hundreds of planets out there, and we suspect there are probably thousands, if not millions of planets waiting to be discovered. So we're in a very exciting phase of this development. So this is just a snapshot as this field develops. And there are no shortage of places for exoplanets within our galaxy. When you look up in the night sky, all of those stars are part of our Milky Way. A lot of them are very much like our sun, and they're all potential sites for other planetary systems in orbit around those stars. So there are 100,000 million stars in our galaxy. And when you look at our galaxy, you've got to remember it does change and evolve, obviously on timescales of millions of years, much longer than human timescales. But it does change, and stars are being born all the time. Particularly in the flat plane of the disk, you can see these wonderful spiral arms. These are where you've got kind of diffuse hydrogen clouds, and then a wave of density moves through the gas, compresses it, and triggers star formation to start occurring. So you can see regions of active star birth and star formation within a galaxy, well, certainly a spiral galaxy. From these spiral arms, you have knots of blue star clusters that trace the arms. Those are blue because they're very massive stars, which are young stars. They're marking out young star formation. And around each of them, you can also see sort of pink blobs of gas. If we just zoom in on one near us in our own galaxy called the Rosette Nebula, here's a young cluster of stars about 4 million years old, and it's still within this gas cloud that it's collapsed from. And it's glowing pink because all the light and energy from the stars is exciting the hydrogen atoms, which then give off this characteristic pink colour. So not all the material that's in the gas cloud goes into that first generation of star formation. Now, one of our closest regions of star formation that we can see, it's only about 1,500 light years away, is in the Sword of Orion. It's the Great Nebula of Orion. It's what you can see with your binoculars, if it was clear tonight, very clear, because it doesn't look quite as pretty as it does through the Hubble Space Telescope here. But buried deep within these clouds of dust and gas here, there are a whole horde of very young stars. They're all about less than 1 million years old. And some of them are really at that sort of crucial stage where they're kind of almost like protostars. They haven't quite evolved to become your standard main sequence stars. And when you zoom in to areas within this Orion Nebula, I've mentioned these before, but you see these wonderful protoplanetary disks, or proplids, around a lot of these forming stars. Here's just a gallery of the proplids. And what you have to realize is that these are cocoons of gas and dust, and they're probably hundreds to perhaps up to 1,000 astronomical units across. Now, an astronomical unit, I'm going to be using that a lot, that's the distance between the Earth and the Sun. It's 150 million kilometers, but 1 AU is the Earth-Sun distance. And so these are kind of larger than our solar, a couple of times larger than our solar system, and they're kind of cocoons. And at the center, you have a star forming. And you see these cocoons in two ways. One's like this and one's like this. This is where perhaps you can see the protostar at the center, and the cocoon is absorbing, is obscuring most of the light of the star and any background light from the gas. Other times they're being lit up by other stars, they're shining on the cocoon, and the outside of the cocoon is being illuminated. So at the core here, you've got the protostar, and it's surrounded by this cloud of matter. And a star will form from dense pockets within a gas cloud. Your gas cloud gets squeezed. Gravitational collapse under self-gravity is going to happen where there are densest pockets within that material. And these sort of compress down to form these cocoons. And right in the middle, You maybe got a slight higher density of material, you've got more self-gravity. Matter from this little cocoon, this little pocket of denser region, rains down to the centre, heats up through the gravitational energy released, and at the centre you're going to form eventually a star. But not all the matter within that little envelope accumulates onto the star before it starts to heat up and becomes, the protostar. At some point it's going to heat up and material will no longer accrete onto it. So in the same way that the birth of the stars doesn't use the whole of the gas cloud they're forming from, the birth of a star doesn't incorporate all the material from that little pocket it's formed from. And all that material around it is what goes on to eventually form the planetary system around that star, if it survives. Of course, Orion Nebula is quite harsh. You've got lots of winds and things from other bright stars which might erode the disks. But in an isolated environment, that pocket of material will then gradually settle down to form a planetary system, just like we think our sun did about 4.5 billion years ago. So what we're looking at in the Orion Nebula, artist's impression, obviously, until we get the James Webb Space Telescope, we're not going to have brilliant pictures like this. But you've got it's like a thick torus of dusty, gassy material. Now, most of the matter's gone into the sun, or gone into the star at the centre. This is only a few % of the total material that's available in the cloud. It's mostly gas, and there's about sort of 1% of the mass is in small particles of dust. And the star and the cloud around it kind of share the same composition. They form from the same pocket of gas. It's like 3/4 hydrogen, quarter helium, and then like a little smattering of heavy elements. And those heavy elements are either locked into compounds of the hydrogen, molecules, or perhaps they're forming silicates and carbonates, and those are the dust particles within the gas cloud. And those dust particles are crucial for the formation of the planets from the cloud. Now, obviously, our impression of how solar systems form is very much guided, or has been for a long while, by what we see in our own solar system. We have a very clear pattern of planets. Okay, so the planets are not to scale in terms of distance out from the sun in this diagram, but you get the idea that closer to the sun you have the small planets. These are the rocky, silicate, metal planets with very thin atmospheres on the surface. These are the warmer planets. Further out, beyond the asteroid belt, you get the gas giants, things like Jupiter, Saturn, Uranus and Neptune, where you've got a rocky core, and on top of that you have this enormous helium and hydrogen atmospheres around that core. And this flavours how we think planets form from this original proplid, if you like. This is called a nebula theory of planetary formation. We call that the original solar nebula. And it's because different planets form at different places in that original disk. Think back to the proplid around the star. You're going to have a gradient in temperature. It's going to be warmer near the star. It's going to be cooler out to the edges of the nebula. The further away you are from the star, the cooler that proplid is going to be, the disk is going to be. Now, right close into the sun. Now, you think of the star. It doesn't immediately become a main sequence star. It takes several million years to change from being powered by sort of gravitational energy to actually nuclear fusion beginning, and it can be quite unstable. But nonetheless, it's hot, even if it's not quite a proper star yet. And the energy it produces blasts the inside of this proplid. It breaks apart those molecules to their constituent bits, which will then get blown out to the outer regions of the nebula, because they're lightweight, and it also evaporates all the dust near to it. So you get this segregation both in terms of temperature and composition within the nebula. On the inner part of the nebula, you have a big gap around the star where everything's been blasted, and then it cools down and you have the most readily condensable material. So this is where you've got the silicates and the metals start to condense. Then a bit further out, the nebula cools down enough, and within our solar system, that's at about 4 times the Earth-Sun distance, 4 AU. We have a region we call the snow line, when the much more volatile, icy materials can start condensing. So that's things like carbon dioxide, water, methane ices. And so you have a lot of the volatile materials further out. So when you think of that with respect to the planets that form in our own solar system, these dust particles build up to form the planets. So within the snow line, the inner parts of the nebula, dust particles, perhaps they start sticking to each other through electrostatic forces, and you build up enough mass that then's got a slightly bigger gravity, pulls in other dust particles, and you start by this aggregation of particles to build up to planetesimals and, small pebbles up to rocks a few kilometers across, to planetesimals, to protoplanets, just by aggregation of material. Out beyond the snow line, though, is a slightly different matter, because you've got these dust particles, but they've got more mass because they've got all the ices that have condensed onto them. They can build up together to form much bigger protoplanets and rocky objects, things maybe 5-10 times the mass of Earth. And because they're in this cooler part of the nebula, they've got enough gravity to then sweep round and accumulate lots of gassy material from all these volatile compounds and build up those huge atmospheres. Now, this is all going on, while the star is evolving. So it's the same process, small objects closer into the sun, larger, more massive objects further out. And you settle down to the segregation of rocky planets close to the sun, gas giants further out. And the gas giants will carry on accumulating material. Jupiter and Saturn will accumulate material a lot faster because they're in a denser part of the nebula, so they'll grow more massive. Uranus and Neptune, they're slightly less dense. They don't accumulate material so well. But you come to a point where all planetary formation stops because the star finally becomes a main sequence star. Nuclear fusion begins. It's going through this unstable phase, and it gets to a point where it blasts out all that remaining volatile hydrogen, helium gas within the nebula. The planetary formation stops, and you've got the segregation, the types of planets you get. So this is our kind of working model that's informed by our own solar system. Okay, this is going to change when we'll revisit this by the end of the talk, and you see how we have to evolve this idea of how planets form. So you can have planets forming while the star switches on. And the disk itself, the volatile material gets blown off, but the disk itself evolves to something called a debris disk, which is wider and flatter. I mean, we're going to move to a lot of artists' illustrations, by the way. A lot of the data, of course, don't produce real images, but these are scientifically inspired artists' impressions that are trying to convey the things that we think we're seeing. And the debris disks are made of dust and not gas. And they're much flatter and much wider, and they're found around stars that are generally less than 10 million years old. And here's an example of one. This is a pitch taken in the infrared, which is why it's these garish colours. And you've got a problem that there's a star at the centre of this disk, because, the disk is thinned out. You've exposed the star. You've got all that bright starlight that, is too bright. So here you have a mask that blocks out the starlight, and that's part of the mask. But I hope you can still see there's a line along here of light that is one of these disks seen edge on. And to give you an idea of scale, if that's the size of Neptune's orbit, we're talking about something that's way beyond where the normal planets are. And now, these disks, you can see, some of them produce a bit of infrared light. They also reflect the light of the star, and you can analyse through polarization filters the way they reflect the light of the star. You can work out something about the nature of these particles. What you find is they're dust particles, and they're quite fragile. We don't expect them to last long. They're easily evaporated, easily sputtered. So to have these enormous disks out beyond the planets, they have to be continually replenished. And we think all of these lightweight dust particles come from collisions, because we built up protoplanets inside around the star. These protoplanets are still colliding and evolving and aggregating and kind of fighting it out to see who's going to be the final planets around the star. There's a lot of collisions, there's a lot of lightweight dust given off, debris within those collisions that then gets pushed out by the stellar winds out to the far regions beyond the planets. And these debris disks, we think, are a very good sign of where there might be young planets. And in particular, if you look at this disk, it's not uniform. It's more bunched up at this side compared to this. Maybe this is due to some gravitational disturbance by a giant planet. And it is possible to see both disks and planets coexisting around a star. Now, Fomalhaut is a very bright star in the southern sky. It's only 25 light years away. Again, we've blocked out the light from the star in this Hubble Space Telescope image with a mask. There's a lot of scattered light coming out, but I hope you can see it's surrounded by an enormous debris ring. And that's about sort of 24 to 30 billion kilometers out from the star. Now, there's also a planet here in this image. Okay, the star's here, and I'm willing to bet quite some money that you can't spot it, because it is that little thing. And we know it's a planet because it moves. It's not just a glitch in the data. When you re-observe, you see this thing progressing along an orbit. So you have a giant planet. It's about 3 billion kilometers in from the disk. And if you plot that orbit, it's got a very elliptical disk, perhaps taking about 2,000 years to go around the orbit. And perhaps the gravity in it is shaping the very sharp inner edge of that disk. And if you project its orbit, assuming it's actually the same plane as the disk, it should actually encounter that disk in about 20 years' time, which you might expect to be slightly destructive. So we're curious what's going to happen to this planet. But this is a big planet, 3 times the mass of Jupiter, and found just within this debris disk. And it's not the only one. Here's another example, Beta Pictoris. There's again, you've occluded the light of the star, there's a disk, and again you see it's not a completely flat disk, it's got ripples, it's got rings, it's got distortions, again perhaps due to material bunching up, due to the gravitational influence of planets within, close to the star. And so the disk was first detected, and then later observations where you're masking out the star a bit more effectively reveal a giant planet, 8 times the mass of Jupiter. It's about 8 to 15 times further out than the Earth is from the Sun. And it's taking, it's probably somewhere like the orbit of Saturn, 35 years or so to go once around its Sun. So we can see the planets, and these disks are a great indicator of where to look. But it's only really effective quite nearby to look for them using this method. So let's go on to how you actually detect exoplanets. And there's a myriad of ideas and a myriad of ways. The most obvious one you think might be direct imaging. Just take an image and look for your planet. And how you see a planet, whether it's in our own solar system or one of these other solar systems, is because it reflects the light of its host star. Now, obviously, we see the moon because it's near to us, it's big in the sky, it's bright. We can see that in daytime. But remember, we can't even see the reflected light of the other planets on our solar system when the sun's up, because they're too faint. The sun, you can see them at night when the sun's not in the way, but during the daytime, the sun's too bright. Its glare masks out anything from the stars. So if that's true in our own solar system, you can imagine it's true in other solar systems. The light from the host star outshines the planet by anywhere between 1 million to 1 billion times in terms of the contrast in brightness. And the other problem is that the planet, you want to see planets that are quite dim and quite close to their star. You really don't want to detect just these ones that are a long way out. You want to detect the ones that are close in. And it gets even harder to see that light when it's close into the star. So this is quite a challenging proposition, even with the biggest telescopes and adaptive optics, to try and just detect spots of light around stars. Now, you can, be crafty and do this in the infrared, where maybe, first of all, you look for dimmer stars to decrease the contrast between the light of the star and the planet. You maybe look in the infrared, where the planet contributes some emission of its own and the star is dimmer, and that reduces the contrast to perhaps 1 million to 1. The problem with that, though, is that the ability to distinguish 2 objects in an image is a function of what wavelength you're observing in, and the resolution is worse in the infrared than it is in the optical. But nonetheless, you can occasionally detect planets around other stars. Now, this is a real picture in the infrared of, you have a very dim dwarf star here, and separated about 50 astronomical units, so that's beyond the orbit of Pluto on our own solar system, you have a massive planet. It's taking about 2,000 years to go once around its orbit. So it is possible to detect them, but there's a bias to finding the ones that are a long way out from the planet, and they're also quite large, so they're producing their own infrared emission and also reflecting more of the starlight. But nonetheless, there's this observation. Here's an observation of a multi-planet system. This is a system that also has a debris disk out further beyond the planets. And again, you've masked out the light from the end of the star, but you've got 4 planets in orbit around it. They're all super Jupiters, 5 to 10 times the mass of Jupiter, and again, they're a long way out, going from about 20 out to probably about 80 astronomical units from their star. So this is a challenging way to detect them. It has detected several systems already, and it's one that people are using because you can still do other kinds of science with these detections, but obviously we employ many different ways. And instead of just dealing with reflected light, you can also look for refracted light due to the process of gravitational lensing. If you have a mass in space, gravity is the way that it distorts the space-time around it. And this influences light, which would normally travel in a straight line. It gets curved through the bent space and distorted. And we see this as astronomers when you have a really massive galaxy and there's a background source, that the light gets distorted into a mirage, sort of arcs and different shapes like that around the galaxy. It's something we observe everywhere. But it can also happen if you have a star. So a star like our sun, its gravity will deflect the light of nearby stars. And this was, what was used to actually prove this prediction from Einstein's theory of relativity, the way that the light from nearby stars were distorted in terms of their positions during a total solar eclipse. But if you have a star that's a long way away and it's lensing the light of another star, you're not going to see these distortions. It will do the lensing, but you're going to produce something else that is called a microlensing effect. Let me explain. Imagine you have a background star, and that's the yellow one, and you've got the Earth in my diagram. And then another star just happens to line up exactly between you and that star, because this is all a moving system. The Earth is moving, the background star's moving, the intermediate star's moving. As they exactly line up, the gravitational field of this star will distort the light from the background star and curve it round. Now, ideally, we would see a distortion, this mirage, but the amount of deflection is tiny, so we don't see the distortion. What we do see, though, is a magnification of the light. Look again at this image. Normally, we just see the light that happens to go along this straight line. Now we're getting the light that would have gone in this direction and this direction. They've got focused towards us, and it's true about the light coming out of the screen and into the screen. You have an amazing focusing effect, which increases the amount of light you see from the background star. And it's just while the stars are aligned, and then the system reverts to normal. So if you track the light of the background star, you'll see it has a ready, sort of steady increase in its magnification and then a decrease in terms of the light output. And that's called a microlensing event, and we observe these. Now imagine the star that's in the foreground also has a large planet around it. You will then affect the lensing you see from the star. So here's your star, and this has got a nice green planet. When the star and the planet both are kind of along the line of sight, you will get extra magnification contributed by the planet compared to the star alone. And then it reverts to just basically being the star's gravity that it's affecting the light. So you have your normal increase and decrease, but when the planet is also along the line of sight, you get this spike of light. And this is an observation of one of these events that reveals a planet around a star. Here's a microlensing event due to the 2 stars. This little deviation is because a planet also happened to pass in the way. And this particular planet, it's a super Earth, 5 times the mass of Earth. It's about twice as far out from the Earth as the Earth from its star, and it's a cool star, so it's actually quite a frigid world. We reckon about minus 200 degrees. So you can find exoplanets this way, and you can find, you're not supposing much about their mass. It's good at finding distant exoplanets because your chances of having that alignment are greater the more depth you look into space. This big problem with this is it's not a repeatable observation. It's a very precise alignment, so you have to survey thousands of stars to perhaps see one microlensing event. You've got to have very precise alignment, and you will see the observation, and it's a complete one-off event. You can't go back and check your data and try and repeat it and get a better signal. So it's very much up to how you analyze those data. So this is a good way of finding planets again, but it's not very efficient. There are two main workhorses in terms of finding exoplanets. One is the radial velocity method, and this is due to the fact that it's not a completely static system. We tend to think of planets go around the star and the star sits at the centre of the planetary system. That's not quite the case. The gravity of the planet, or planets, pull on the star and affect its motion slightly. Now, imagine you've got two equal-sized objects. It's a nice symmetric system, and they orbit around their centre of mass or centre of gravity in a very symmetric situation. But if the relative masses of those two objects change, they begin to orbit around a point that is closer to the more massive object. And if you keep changing this ratio, you start getting to the point, perhaps, where you've got a large planet and a star. The star is moving, but around a position just like within itself. So it's doing what's called a wobble. Our sun does this according to the response to the gravity of Jupiter. It orbits around a point just slightly just outside its surface at a speed of about plus or minus 13 meters per second. It's a wobble. Now, we can't see this. It's tiny. It's not like you're seeing the stars moving to and fro. We don't have that kind of detail. What we can see, though, is we can detect the motion from the Doppler effect. If the star is going round in its orbit, sometimes it's coming towards it and you get the blue shift and it's like it's going away from us and you get the red shift. And you can detect the signal in the lines in its spectrum. So here, as the planet goes round, the star comes towards us and the light's blue shifted, it goes away, the lines in the spectrum are red shifted. And from this, you get an idea, first of all, of the period of the planet, how long it takes to go once around the star, because that's how often it takes the star to go through this wobble. So from observations of the radial velocity against time, so here's a star that's kind of a planet going around it every 3.6 days, you get this very neat pattern of coming towards, coming away. So you've got the period of the star. And you know the mass of the, period of the planet. You know the mass of the planet because how close in it is from its period tells you how fast it's moving, how close it is into the star. It tells you what gravity the star's responding to. You get the mass of the planet. So you're getting the separation, you're getting the period, you're getting the mass of the planet from this observation. Now, the first time this was done in 1995 was around a star called 51 Pegasus, and it was the first exoplanet found around a normal star. 51 Peg B, mass comparable to Jupiter. The problem is it was discovered to have an orbit of only just over 4 days, and that's Earth days, of course. So that means it's stonkingly close to its host star. It's whizzing round, and if you work it out, it's got temperatures on its surface must be in excess of 1,000 degrees. And this was not expected. This is not, you know, the first planet to be found around a star is very different from anything we've got in our solar system. And this is the prototype of something we call a hot Jupiter. Jupiter size, Jupiter mass, but in the wrong place compared to our solar system, whizzing around very close to the star. So this now is a very efficient method for finding, not only discovering stars, but also getting their properties, and discovering exoplanets even, and getting their properties. But you can also apply it to not just normal stars, but surprisingly, also very exotic objects. And the first exoplanets discovered were not found around a normal star, but around a pulsar. And people weren't even looking for exoplanets around a pulsar. Now, a pulsar is a spinning neutron star, and it's got these twin beams of radiation which pass by as every time the pulsar spins. And the pulsar 1257 plus 12 is a pulsar spinning 160 times a second. It's a very regular frequency, very regular clock. Now, just in the same way the light is affected by the Doppler effect, you can see variations in this pulse if the pulsar is moving. And what they discovered in 1992 is from this pulsar, variations in its frequency, which meant it was being tugged around in its orbit by 2 very small planets. And a third one was discovered a couple of years later. And so we discovered planets. The first exoplanets found were around a pulsar. And because it's such precise measurement, you can detect them. They're quite low mass objects, you know, just a few times the mass of Earth and well within the orbit of Mercury, very and comparable, going around their pulsar in a matter of days. And this was totally unexpected. And it's still curious as to how you can get planets around a pulsar. You'd expect them to be evaporated during the supernova explosion that creates the pulsar. It could be that these are the cause of the gas giants. The outer layers of the gas giants got stripped off in the explosion and the core survived to become these pulsar planets. Or maybe they could have formed later from material blasted off from the pulsar explosion. You know, it's not certain. There are various ideas like that. But this is not the only pulsar which has been found to have planets around it. There's a planet around a second pulsar, 1620-26b. It's nicknamed Methuselah because it's round a white dwarf star. It's projected to be at least 3 times older than the Earth. And the curious thing is it's a massive planet. It's about 3 times the mass of Jupiter. It's a long way out from its star. It's much further than Jupiter is out from its star. It's in fact orbit around a neutron star and a white dwarf. They're going around each other. You can kind of see them in the artist's impression here. And it's orbit around both of those. And the speculation is that this was a normal star and it was in orbit around the normal star. The star's gone to a white dwarf. The planet's kept in orbit around it. But they've perhaps both been captured into the gravity of a neutron star, and that's how such a weird system has evolved. This is found in a globular cluster where there are lots of stars, there are lots of interactions between stars. So that's a possible scenario. But again, something very different from what we were expecting. So you can find pulsar planets, but pulsars are rare, and perhaps pulsars with planets are rare. So again, it's a variation of the radial velocity method, but it's not very efficient. And the most efficient way now we have of finding planets is through when they block the light of the background star. If they happen to pass between us and the star, you get the silhouette of the planet that just dims and blocks a bit of the light from the star, you know, from our vantage point. Now this, in the image here, is a transit of Venus. And just seen from the Earth, if Venus moves across the surface of in front of the Sun, it only blocks about 0.1% of the Sun's light. It's a much reduced fraction, of course, if you're looking at a very distant star where you don't even resolve the disk. You're looking for a tiny fraction of the dimming of that star due to the silhouette of a planet along the line of sight. So effectively, what we're observing is monitoring the brightness of a star, and you're looking for just a tiny dip in that brightness as the planet moves across the face of the star. Now, this is exaggerated, okay? There's the zeros kind of way down below the floor here. It's a tiny fraction of a percent of decrease of brightness that we're expecting. But it's a characteristic light curve in that it's fairly flat along the bottom, and it doesn't change once the planet's in front of the Sun. And if you see one of these eclipses, you can learn all kinds of things. You're looking for a repeated pattern of eclipses within the light curve of the star. Every time one of those happens, it tells you how often the star is going around its star, and the exoplanet's going around its star, so you get the period of the exoplanet. You can also tell things about their size. So the time it takes for the planet to just starting to clip the limb of the Sun to moving directly in front of it, this gives you an idea of the size of the planet relative to how long the whole eclipse takes, which gives you the size of the star. So if you know the kind of star it's in orbit around, you can make estimates about the size of the planet. You've got the period from Kepler's laws, you know how far it is from its star. So you can begin to build up a lot of properties about this exoplanet. The one thing you don't get is the mass. This is all sizes and separations. But what you can do, if you observe a transit like this, go and observe it then with a telescope, with spectra, and you pick up with the radial velocity the mass of the planet. And then you're really doing science, because you have the mass and you have the size of the planet. You start to tell what it's made of. You get to know its density. And there's a whole range of densities out there. You know, 2 extremes. This is Corot 3b. It's a size similar to Jupiter. It's got a mass 22 times greater. That means you work it out something like 2.5 times the density of lead. At the surface of this planet, you've got a surface gravity that's 50 times greater than the Earth. Again, very extreme, dense object. And at the other end, you have a hot Jupiter, So it's got less than the mass of Jupiter, it's about twice the size. It's all puffed up, presumably because it's warm, and its density averages out to about 0.3 grams per cubic centimetre. That's about the density of balsa wood or cork. Very lightweight planet. And there you can imagine the surface gravity is so weak, it's struggling to hold on to the outer layers that may well be evaporating off to kind of form a sort of comet stream behind it. So you begin to tell a lot about physical parameters of the planet. As I've mentioned in my rotation lecture, by seeing whether which side of the star it eclipses first, you can also find out that some of these go around their stars the wrong way. All the planets go around the sun the same way direction as the sun spins, and that makes sense if we've all collapsed down from one prop lid. We see exoplanets that go, the stars turning that way. I've got to get this right, it's like patting your head and rubbing your tummy at the same time. Stars turning that way, the planet's going the wrong way around the star. It's called retrograde motion, and that's surprisingly common. There are problems with this method. You've got to have the geometry right, such that the planet crosses between you and the star. And out of all the system with planets, we reckon about 1 in 200 would show the right alignment. So, of course, you've got to monitor lots of stars all the time. You need to monitor their brightness very accurately to be able to detect these tiny dips of brightness, which can be mimicked by other effects. Stars themselves are variable. They're not always a constant brightness. You can have twinkling in the atmosphere that can vary the brightness of the star as it's received by your telescopes. It can mimic the result. And if you've got some activity in the star manifesting itself as star spots, just like the sunspots on our sun, especially if they're long-lived and then rotate repeatedly round into view as the star rotates, that can mimic the appearance of a transit. So you need to build up a whole lot of transit observations before you're really sure that you've detected this planetary system. So there have been 2 missions that have been instrumental in raising the number of transit exoplanets discovered. There was CORO, launched in 2006, a 10-inch telescope in space doing transit observations, and it failed just at the end of last year. But nonetheless, it's discovered a whole host of objects, some of them quite extreme. This was, for a long while, the smallest planet known, 5 times the mass of Earth. Radius only just about 1.5 times that of Earth, but in an orbit of 20 Earth hours. Again, a super Earth whizzing around close to its star. It's going to be boiling hot on the surface, that they try to convey here. With something that looks suspiciously like Australia here. I'm not quite sure about that. Yeah, there would not be, probably molten on its surface. But this was for a long while the smallest planet found. And the first temperate planet found, again, something like a Jupiter, out at a radius just beyond Mercury, with temperatures possibly in its cloud tops, around 0 to 150 degrees, not boiling hot, not freezing cold. So again, it pushed the range of planetary detections out there. The mission that we're all using and relying on now is the Kepler Space Telescope, launched in 2009 with a sort of 3-foot telescope on board. Much better detection in terms of the transit signal. This is revolutionizing our discovery rate. And this is part of why we're in such an exciting period of observation. It's got a much longer depth of view into the galaxy. It's so sensitive, it's now pushing the stars we're looking for planets around out to thousands of light years instead of the few hundreds that have been done previously. And it's detecting them in terms of, at the minute it's stacking up candidates. It will think it sees a transit occurrence, which then gets followed up from ground-based telescopes. But we've now stacking up thousands of candidates from Kepler to be followed up, more accumulating every day. So it's building up a huge wealth of potential exoplanet candidates out there. You can tell other interesting things from the transit observations. Here's one of the first ones detected with Kepler. This is when the planet moves behind the star. This is where the planet moves in front of the star and blocks out its light. There's a secondary eclipse here when the planet moves behind the star and you lose the planet's light. So you get a primary and a secondary eclipse. And this is such a beautiful data set. You can see a sort of modulation here. That's because you're also seeing the phase of the planet. As it moves around the star, now that's a secondary eclipse, and then you've got the primary eclipse as the planet moves in front of the star. It's new, then you get to a crescent, and then you start getting to a full surface just before the secondary eclipse. And so the brightness of the star brightness of the exoplanet changes as it goes around in its orbit, just through the amount of the reflected side you're seeing. So that's the level of detail we're achieving. The other thing, of course, is that during the transit, you can isolate the spectrum of the planet. The planet shines by reflected light, but if it's got an atmosphere, that light is also absorbed and filtered by the atmosphere, and you can look for molecular signals of the constituents of the exoplanet's atmosphere and the spectrum. Imagine, for example, you've got observations when there is no transit taking place. You have the light from the star and the planet. You wait till the planet disappears behind the star. You take the spectrum normally, and then during eclipse, you subtract the two, and you're left with the spectrum of the planet alone. This has been done. We've detected molecules in the atmosphere of exoplanets, methane, carbon dioxide, water vapor, found in objects such as this Jupiter-sized planet, again, very close to its hot star. Not just detect these molecules in its atmosphere, but the fact the atmosphere is evaporating off at like 500,000 kilometers an hour. It's losing about 1,000 tons of material a second, and so it's being blasted by perhaps a very active star with flares on. So again, very different from what we see in our own solar system. So we're stacking up different kinds of planets, things that are not in our solar system. We have the hot Jupiters. Cold Jupiters we have, they're things like our own Jupiter, but we're seeing so many of these really massive hot Jupiters close into the star. And not just ones about the same mass and size as Jupiter, but also super Jupiters, things that are perhaps 5 up to about 10 times the mass of Jupiter. Any larger, we start to call them brown dwarfs, if you like, failed stars. But super Jupiters, again, we don't see those in our solar system. Then, going down in mass, you have their smaller mass equivalents. You have the hot Neptunes, things that are about sort of between 2 and 20% the mass of Jupiter. Again, so Neptune-sized worlds, but again, really close to their host star and hot. And even beyond that, we have another class of planet that bridges a huge gap we have in our own solar system between Earth and Jupiter. We find lots of super-Earths, objects which have a mass up to about 10 times the mass of Earth. And these are getting increasingly common. Here's just an example. 55 Cancri is the innermost of 5 planets, so it's really close to its host star. It's about like a fraction of Mercury's orbit around its star because it goes around very fast. It's got 8 times the mass of Earth. It's only slightly bigger than Earth. But this is a typical super-Earth. And super-Earths are found very close to their stars. They're found slightly further away. We begin again to get slightly more temperate worlds. Here's one, okay, that's again artist's impression of Gliese 667cc. It's orbiting around every 28 days. Its mass is about 4 Earth masses. Start getting slightly cooler than 55 Cancri. And you don't just see them in isolation, you see them in planetary systems. We're detecting well over 100 different multi-planet systems. Kepler 11, you've got 6 super-Earths to Neptune-sized planets, and they all orbit within the orbit of Mercury within our own solar system. Very complicated systems to try and disentangle all those transits from all the combination of planets. We see planets in orbit around double stars. That's relatively common, this idea of Tatooine. Here are just a couple of examples from Kepler, where you have planets that orbit around the star, 289 days, 131 days, but then you have 2 stars at the centre in orbit around each other in a matter of, just 2 or 3, 4 weeks. There's another system here, Kepler 16b. This is like a Saturn-sized planet in an orbit about as close as Venus, and it's orbiting again around 2 very different stars that orbit each other in a matter of days. Now just think what it must be like on a planet like this, the range of seasons you must get, and how the conditions, especially if it's in a very eccentric orbit, is changing all the time. Planets like that are going to be very different from the planets in our own solar system. And the best case is one that was announced fairly recently. This is the first one that's been discovered by citizen scientists working as part of the Exoplanet project, finding potential candidates from Kepler. This is where you have, again, a Neptune-sized object represented here. It's very massive. It's 170 times the mass of Earth. It's got a 138-day orbit around again, a binary system. They orbit each other every 20 days, and they are in orbit around another binary system of stars. So you've got a planet in a quadruple stellar system. How long can that last before it's torn apart by all the various gravitational fields? Again, things that we would not expect are beginning to be commonplace. So the tendency has been that the first planets you find are the most massive and the bigger ones that are closer into the star. These are the ones that are going to produce, they're going to block most of the light or produce the largest tug in the radial velocity method. They're the ones that have the short periods and are going to be picked up first in the data. We're now reaching the stage where the mission has been going long enough, the stars are being monitored long enough, you're beginning to pick up both smaller variations in brightness, so smaller planets, and also ones that are orbiting on longer time scales. And we're beginning to get closer to Earth-like planets. This, for example, is a very recent, I think just from the end of last month, is the discovery of the smallest exoplanet yet, 37b. It orbits, okay, really close to its star every 13 days, but its mass is between that of the Moon and Mercury. Smallest exoplanet yet. Too hot for anything like life, but it's still getting down to, it's now beginning to open up a new area of exoplanet exploration, and one that we're going to find more and more of these small exoplanets. But of course, what we want is the Earth's twin. That's what everybody's interested in. That's the next stage. And there are some good candidates. The standard one for a long while has been Gliese 581. This is a system with several super-Earths around it. So if this is distance out from the star, here we have our sun and all our planets, and this blue streak marks the so-called Goldilocks zone, where water would be liquid. We expect the temperatures, temperate temperatures, such that between, ordinary pressures between 0 and 100 degrees, you might get liquid water if it's on the surface of that planet. Now, Gliese 581 is dimmer and cooler, so the habitable zone is closer into the star, and potentially two, and certainly one of its planets seemed to lie right in the habitable zone. But it's still a huge super-Earth. It's still not quite Earth. And this has been the classic case of the most habitable planet. But again, things are changing very rapidly just over the last few months. So about a year ago, we would say Kepler 22b, represented here, is slightly bigger than the Earth, was our best case. It has a year that's 290 days, well within its star's habitable zone. So even though it's bigger, if it's got water on the surface and it's a rocky planet, it could be liquid. And because the temperature, we guess, would be around 20 degrees. But we don't yet know really whether that's a rocky planet or a gas giant, because it's just that strange size we don't know so much about. And even just last, I think it was January, was announced the best candidate yet. Now, this is just a candidate. KOI means Kepler Object of Interest. They have yet to confirm it. But if it is confirmed, you've got something that's only half as big as Earth, a similar orbit to Earth, 240 days, slightly further in, but again, it's a slightly dimmer, cooler star, could be very similar to conditions on Earth. So this is where the barriers are coming down right now. I expect over the next few months we'll see even more changes, even more candidate twin Earths being found. So this is kind of the current tally. You will see we've got of the order of over 800 planets found in over 680 systems, and many of those are multiple planetary systems. Transit dimming, radial velocity are the workhorses. They're producing the discoveries. And just look at the way that the rate of discovery is changing. The first ones were found in 92, 95. We're increasing the number of planets found. Given that this is 2013, and we're not very far through 2013 yet, you can see it's changing rapidly. At first, if this is distance to the star, and this is the year of discovery, we found relatively nearby objects. But now with Kepler, we're finding objects that are further and further away. Again, this is date against the mass. At first, we only found the very large, very massive objects. They're the ones that come out first in the surveys. But now the mass range being discovered is being extended and right down to Earth-style masses now. So you can see we're broadening the whole properties that we're discovering. And while there may be concentrations as mass against orbital period, there was a tendency to find very massive objects close in, within a few days of the star in terms of orbital period. We're now broadening that out. And also there's a concentration of Jupiter-like objects. So this is mass against radius, and that marks the Earth. Again, all of this is changing. We're discovering more and more objects and a wider range of objects. And of course, the bottom line is we're not finding things like our own solar system. Our solar system is unusual. It doesn't have hot Jupiters. It doesn't have super-Earths. And let's just go back to these hot Jupiters. We see them everywhere. They're incredibly common. And the question is, how do you get a hot Jupiter? We still think they have to form out beyond the snow line. So you've got the volatiles that accrete to make that atmosphere. You need some extra evolutionary mechanism that shrinks their orbit and brings them in towards the star to become from a cold to a hot Jupiter. So you need some migration mechanisms. And one that happens, we think, is because the planets form within a disk, they're accreting material from the disk. Their gravity sets up, it kind of affects the material in the disk around it. This is a simulation where you're looking, there's the sun, this is a planet forming, and this is just showing, and this is just focused on the planet. It's accreting matter within the disk because it's still forming within the disk, but its gravity bunches up that matter into a kind of spiral shape, which in turn exerts a torque and a gravitational influence on the star. So the inner bit wants to kind of push it outwards, and the outer distortion wants to push it inwards, and that's slightly bigger. And so this torque gradually pushes the planet and migrates in towards the centre of the solar system. It's all gravitational interaction between the planet and the material in the disk. And as it goes in, it's also gobbling up material, accreting material from the disk. The migration slows down as it clears a passage around it because it accretes all the nearby period. The formation of the planet also stops at that point. Slows down at that point, but it doesn't stop until the star gets active and blows away the rest of the disk at the end of the proplid phase. But at that point, over quite quickly, through the interactions between the planet and its disk, it's migrated close into the star. But you still get planets that are going the same way as they are around their star. So there may be other evolutionary mechanisms. For example, if you have planets, lots of giant planets, they will undergo gravitational influences, they're going to go collisions that maybe will send one ricocheting out into space and the other one in a highly eccentric orbit that's getting knocked retrograde. So we need a combination of migration mechanisms to affect the orbits of these Jupiters, sending them close into the sun, sometimes sending them retrograde and sometimes sending them quite wayward. There are other things as well. Just because you find an Earth-like planet at an Earth-like radius from a Sun-like star doesn't mean it's like an Earth. Because to get an Earth, we think you need water. And that could also be quite a fragile set of circumstances. When the planet forms, there are no volatile compounds. It's molten. We think the water on Earth is delivered later, but in a period we call the late heavy bombardment, when lots of comets from the Kuiper Belt and beyond crash onto Earth and deliver the water. What seems now is that Jupiter, massive planets like Jupiter, are crucial for that event because their gravitational disturbance stirs up the comets and sends this late heavy bombardment and all the water delivered to Earth. We are now detecting, again, this is just from last year, systems, if you look in the infrared, around 2 planetary systems, both of which have super-Earths but no gas giants, no really massive objects. They have comet belts, like our Kuiper Belt, that are 100 times more mass in them. It seems like the comets have not had this big bombardment. They've actually stayed out there. They haven't been perturbed. And so maybe they had, you've got a more gradual rain of material. You've not accreted that material to form liquid on the surface. So again, there seems to be a correlation between properties of the cometary belt, perhaps, and whether or not there's a gas giant on the, and whether that ever turns the world Earth-like. So there's so much more yet to discover. We even have, probability of rogue planets. If some of those collisions send planets hurtling out of the solar system, we should still be able to find planets out there that are unattached to stars. And so far, by a survey of millions of objects, there's been one good candidate found for a rogue free-floating planet. But again, we should expect many more of them out there, but they're very difficult to see if they're sitting in isolation, well removed from a star's light and gravity. So there's a lot yet to happen. Kepler is going to be continuing to gather data, carrying candidates that are then going to be followed up even when Kepler's demise is reached in 2016. We're going to begin to do stats about different kinds of solar systems, how they're influenced by the presence of a Jupiter, what kind of star, star's metallicity, age, type of star. But there's so much more that's going to happen. And the really exciting thing is then going to happen with the James Webb Space Telescope later this decade, which will allow us to see this process of planetary formation within the proplids in even greater detail. So remember, this is just a snapshot. This is an evolving and a very fast and a very exciting field. So keep your eyes posted in the headlines. So that's it for Exoplanets. Just to remind you, got one more lecture this year, going from the very small to the grander scale. Going to be talking about what happens when galaxies collide on the 17th of April, and hope to see some of you there. Thank you.